Well, hello and good afternoon. Hang on a second. Oh, I see. There's going to be a fire exit speech first. If the fire alarm goes off,
hello, ladies and gentlemen. My name is David Bell. I'm the Vice-Chancellor here at the University of Reading, and I'd like to welcome you to the Great Hall for this very special occasion. Given the theme, I can think of no more appropriate venue than the University of Reading to be having this debate and discussion. The University of Reading has been at the forefront of building understanding about the mechanisms and impacts of climate change for decades. Our Department for Meteorology, founded 50 years ago, is now a world-leading centre for research and teaching in weather and climate. Our academics play a major role in developing understanding of the mechanisms of climate change. Not only that, they contribute widely to public policy debates and public communications. More widely, the university's world-renowned expertise in agriculture, food security, soil sciences and the like on the impacts of climate change set us apart. And we are pleased to be recognised in so many different ways, including the conferring by Her Majesty the Queen in 2013 of a Regius Professorship in Climate Meteorology and Climate Science on one of our panellists who is here today, Professor Keith Shine. Professor Shine is one of 4 fellows of the Royal Society working on meteorology and climate science at the university, the others being Professor Sir Brian Cox, also on the panel, Professor Ted Shepherd and Professor Mike Lockwood. I'm sure that we are about to have an interesting and thought-provoking afternoon, so without further ado, let me now welcome your host for the afternoon, Professor Brian Cox.
Thank you. Well, thank you. Good afternoon. I'm Brian Cox. I'm Professor of Public Engagement at the Royal Society, which is the UK's National Academy of Sciences. And this is the first in a series of events which are called Science Matters, and they aim to discuss important scientific topics. And we start the series, as you've heard, by talking about climate change. Now, climate change is a complex scientific subject. It requires an understanding and analysis of large amounts of data collected over many decades and detailed modelling. Having said that, however, there is a simple message, which is humans are changing the climate of the Earth. And this statement is not controversial from a scientific perspective, but it is controversial politically, although having said that, all major parties in the UK now accept this scientific consensus. Absolute certainty, however, is not a part of science. As new data is gathered and new understanding develops, new predictions emerge. Science is a fluid subject. It delivers an ever-changing picture of the world. No detail is ever settled or certain. And also, statements from authority are always to be treated with suspicion. The Royal Society's motto, indeed, is nullius in verba, on nobody's word. So, given all this, what is the average citizen to make of climate change? Well, we're here today to talk through your questions. All the questions I asked will have been submitted by members of this audience, and we're going to try at least to answer as many as we can. Now, I'm hosting the event. I'm not giving the answers. I'm a particle physicist, but I do have 4 climate experts here. So I would like to now invite them to introduce themselves.
Thank you, Brian. I'm Brian Hoskins. I'm a professor in the meteorology department that the Vice-Chancellor talked about and have been for 35 years, I think. And I'm also at Imperial College, where I've led the Grantham Institute, and I'm now chair there. So I'm a mathematician by training, and I got into understanding how the atmosphere, the weather systems, and the climate systems work. And that's what my research has been about over the years. And so this is extremely important in climate change, where you're looking at a change of the system to actually try and understand how the system works and then why it might change in the manner we're talking about. So that's my interest over the years, and the picture we were asked if we wanted to produce an object or a picture, and I chose one from the early days of my research in the late 60s, early 70s. We had these Apollo pictures of this planet, and they really were startling and showing the beauty of this planet and also the power of what was going on. So you can see the weather systems in the southern hemisphere there. You can see the tropical convection. You can see the ocean. And you can see the impact on land, on Africa, where in the regions where the tropical convection occurs, then there's green underneath, and then you can see the desert regions either side. So it shows the power of the climate system. This is the Earth on which we live, and this is the system that governs how we can live.
Hi everyone, I'm Kate Jones, and I'm a Professor of Ecology and Biodiversity at University College London and Zoological Society of London, London Zoo's HUE. I'm actually not a climate scientist at all. I'm a biodiversity scientist. And being a biodiversity scientist, it means looking at the global patterns of living things, so wild nature, and understanding the processes that produce the patterns that we see on a global scale, and then thinking about how to think about what processes drive those patterns so we can think about how to predict into the future. Now, climate change is just one of the drivers which is threatening wild species, and it's a really important thing to think about because it exacerbates some of the problems that we're seeing with declines of wild nature. So my most recent work has been looking at how vectors of disease are going to be influenced by climate changes and land use changes and human population increases, to think about how that changes our understanding of diseases like Ebola or SARS. So I really got into climate change and wanting to know more about that because, and biodiversity loss, because I originally did a PhD on the evolution of bats. So you think it's a little bit esoteric, but I bumped into one of the leading conservation scientists in the world, and I had lunch with her, and she said to me, and she kind of outlined the state of nature and how important it was to try to find solutions and trying to do more predictive modelling about that. And that's why I suddenly realised that the evolution of bats wasn't that interesting after all. And I really wanted to understand that. So we were allowed to bring an object or a picture, and I brought Mumble from Happy Feet. So this is actually an emperor penguin chick, and I did a lot of maths on the web last night. It's actually real life size as a newly born chick. And the story I wanted to tell you about that is that these species are threatened with climate change as the ice pack decreases under different models, although they might be under dispute. We were discussing that earlier. But I think the key point I wanted to make was that climate change effects on biodiversity are really complex. So there are impacts on the krill that these species eat, but also with pollution, and that some antibodies of diseases of chickens have been found in these populations in the Antarctic, possibly from human visitors to these places. So climate change exacerbates some of these already threatening processes, and that's the kind of point I wanted to make about complexity. Thank you.
Hi, I'm Oliver Morton. I'm not a scientist, I'm a science writer and editor. I'm currently working at The Economist. And when I started writing books, I realized that I really like writing about planets. This may be a sort of like misbegotten youth spent watching too much Star Trek and such things. But I find planets really interesting because they're utterly scientific objects. They're scientific in the same way an atom is. And at the same time, they're very human because the idea of a world, of a big sphere, is something where we can let our imaginations play. So I wrote a book about Mars, great planet, thoroughly recommend it. The other planets nearby are not as interesting as Mars except for the Earth. And so I decided to write a book about the Earth that was about an aspect of the Earth that's just as real as the oceans and the continents, but isn't thought about in quite the same way. So I wrote a book about photosynthesis, about how plants power this planet that we live on and make all the other life on it possible. And that took me, I was writing about climate change anyway, that took me into the idea of writing a book about what humans are doing to the climate. And I think I've got a picture too. Have I got a picture? Yes. So this is how I got here today, and this is I think this is a lovely counterpoint to Brian's picture, because this is the Great Western Railway, as pictured by Turner in the 19th century, and one of what is obviously one of the greatest pieces of British landscape painting. It's also unlike any landscape painting that could be done before the Industrial Revolution, because what Turner saw, and what Turner gave us in an image, which we also know from intellectual history and which we actually feel, is that there is no longer the sharp line that there was before between what is human and what is natural. There is something running through this world that Turner shows us. There is a change running through it. You can no longer tell the difference between the natural rain and the artificial steam and the speed with which they mix together. The science of steam engines was the science of thermodynamics, which turned out to be the science of the world. And there's a way in which in the 19th century, not only do humans change the world by introducing steam engines into it, they change the world by making it, and our role in it, a steam engine. We are inside a world that we are making artificial at the same time as we put artificial things into that world. That's the sort of approach that I think really helps you understand the enormity of the transformations in the world and the planet that climate change is bringing about.
Right, good afternoon, everybody. My name is Keith Shine. The Vice-Chancellor's already introduced me as the first Regius Professor of Meteorology and Climate Science here at the University of Reading. I'm very happy to be here, and I'm happy that the Royal Society organised this event on a Saturday afternoon to coincide with an international break in the domestic football season, so thank you. I studied physics at Imperial College London, followed by a PhD in meteorology in Edinburgh. And after spells at Liverpool and Oxford, I moved to Reading about 30 years ago with the support and encouragement of Brian Hoskins here. And I teach and research climate science, and my main focus is in quantifying the human and natural factors that initiate climate change. I'm never quite sure how I got into meteorology. During my teens, I remember my father asking me what I wanted to do when I grew up, and something possessed me to say, meteorology, and that was it. But also during the 1970s, I was greatly influenced by some compelling TV science programs by Brian's predecessors, which started to talk about the natural and human forces that shape and change our environment. And so when given the chance to study the topic, I grasped it. I don't want to give away my age, but a few weeks before I was born in March 1958, there was a major event in climate science. A far-sighted American scientist called Dave Keeling started a set of measurements of carbon dioxide in Hawaii that continue to this day. And for many years, it was the only such set of routine measurements. And the Keeling curve, as it became known, has documented the increase in carbon dioxide ever since. And in the meantime, polar scientists have drilled deep into the Antarctic ice cap, and from looking at the air trapped in these ice cores, they have reconstructed a record of atmospheric CO2 stretching back almost 1 million years. And so this plot shows that ice core record going back nearly 1 million years, and the Keeling curve I just talked about is that sharp spike compressed into the right-hand side. And so my striking fact is this, that during that almost 1 million years, from the depths of the ice ages to the so-called interglacials, CO2 never varied by more than 130 parts per million, which is the unit showed here, and it never over that period exceeded 300 parts per million. But in the blink of an eye on the right-hand side of that plot, and in the time since I was born, the CO2 has leapt up by more than 25% to 400 parts per million, mostly because of our burning of coal and gas. And also over that same period of the Keeling curve, that spike at the end, the global surface temperature has increased by 0.8 degrees C. And The 2013 report of the Intergovernmental Panel on Climate Change concluded, after assessing the evidence, that it was extremely likely that the dominant cause of this rise is human activity, and primarily the change in CO2 documented in that spike at the end. So thank you.
Well, thank you, panel, for those introductions. And actually, we have a question on that, Keith, which I might just jump in and ask, which is 400 parts per million. So it sounds very small, and indeed it's true. So CO2 comprises a tiny proportion of the atmosphere. And Mike asked, because of that, because CO2 is such a tiny proportion, how can it have such a huge effect?
Yeah, well that's right. So CO2 makes up 0.04% of the Earth's atmosphere. But the effect of these gases on the Earth's atmosphere doesn't just depend on their amount. It depends on their ability to absorb and emit infrared energy. And in fact, nitrogen and oxygen, which make up 99% of the Earth's atmosphere, have only an indirect impact on the Earth's temperature because they don't absorb very much infrared energy at all. So by contrast, CO2 is very good at absorbing infrared energy. We know this from detailed measurements in the laboratory and in the atmosphere, and as we speak, there are satellites orbiting the Earth looking down at the energy emitted from the Earth, and they can see this signature of where CO2 is absorbing lots of energy. But another point about this 0.4%, it might sound a tiny fraction, but it still means that in a cubic centimetre, here I have this cubic centimetre, there are 10,000 trillion molecules of carbon dioxide. So it's still a huge number, and because these are so effective on a molecule by molecule basis, they do absorb a lot of infrared energy.
There's an amazing calculation by an American climate scientist, Ken Caldera, and one of his students, where they compared the energy given up when you get one carbon atom out of a fossil fuel by burning it, with the energy trapped in the atmosphere by that one carbon atom once it's become carbon dioxide. And you think about the huge amounts of fossil fuels that we burn. It turns out that the energy that we're getting from burning the fossil fuels on a carbon atom by carbon atom basis is only 100,000th of the energy that's being trapped in the atmosphere by the carbon dioxide. You trap 100, and this is because the carbon dioxide stays in the atmosphere so long, you trap 100,000 times more energy with the waste product of the fossil fuel than you get out of burning the fossil fuel. I think it's incredible.
Perhaps I can just give a different perspective on the same thing. The average person in this country produces nearly 10 tons of CO2 per person per year. So we're actually producing a lot in our activities. It gets very diluted in the atmosphere, but there's a lot there.
I think this also goes on to a broader question, which was asked by several people, Sarah, Ruth, Joe and Alan, all asked, are humans really having an impact on climate? You've obviously argued through the CO2 levels that we are. But this question of, or is it a natural cycle? Because there are natural cycles. So I suppose, how do we disentangle the natural cycles from the things that we are causing?
Yeah, well, we know climate has always been varying. The picture up there showed the ice age cycles going back 1 million years. And so, yes, how do we know that recent climate change is due to human activity? And so to explain climate change, not only do we have to rule in human activity, but we will have to rule out natural causes as major contributors. And this all requires a lot of detailed observations and detailed calculations. But the main factors that the main natural factors that could cause climate change over a short period are changes in the energy emitted by the sun and the tiny particles that get put high up into the atmosphere when we have a really big volcanic eruption. And also, even without these factors, that the atmosphere and the climate system would vary sort of on its own. So we have to do these detailed calculations of the impact of carbon dioxide and the impact of other aspects of human activities. And the kind of conclusion is that if we look earlier in the 20th century, say before 1950, the smaller temperature changes we were seeing there could have been part human and could have been part natural. But if we look at the climate change since the 1950s, they're much larger changes, and it's simply impossible to explain those climate changes based on natural factors alone. In fact, there'd be very little temperature change, we believe. And so this is the origin of that IPCC statement of the extremely likely that human activity is the dominant cause.
There's another point that just goes into sort of like just the basic nature of science, is that you should trust things more when people predict them before they happen, and then they happen. And people looked at the climate system, going back to the 19th century, back to Tyndall and Arrhenius, and then in the early 20th century, a guy called Callan, looked at the system and said, you know, if carbon dioxide builds up in the atmosphere, then the world's going to get warmer. And for a long time, people kind of accepted this. They just didn't think that carbon dioxide was going to build up in the atmosphere. And it was actually the PhD supervisor of Dave Keeling, who's part of whose graph you just saw, who said, you know, actually, this thing we thought that was happening, whereby the ocean was using up the carbon dioxide and it wasn't building up, that's not happening. Carbon dioxide is beginning to build up, and so it will get warmer. And then, after he had said that, he set Keeling on to measuring carbon dioxide, and Keeling showed that carbon dioxide continued to go up, and it did get warmer. Now, obviously, coincidence doesn't prove causation. At the same time, when someone from first principles predicts that something is going to happen if such and such another event takes place, and it then does, and it comes out pretty much as they expected, that's a very strong, visceral argument for why you should take it seriously.
I just wanted to add that we're always looking at a mixture of natural variability as well as what may be due to human activity. And if you look at the Ice Age interglacial cycle that Keith was showing, that's certainly a huge background natural variation. But we're taking the system at one of those warm points and we're turning up the radiator suddenly. So we're on a warm spot in the natural cycle and we're making it even warmer. But the more you come to the local, the more the natural variability seems to come to play. If you go back to the December of 2010, which was incredibly cold in the UK records, and there was one day when I know in London the temperature wasn't going above freezing, and I looked at it in Greenland, it was plus 10 that day. You know, so we're looking at patterns of things that occur, and there's pluses and minuses. But what we're doing to the system does show globally very clearly now, and even locally it's starting to be clear as well.
Yeah. Just one other point is we don't just look at the temperature at the surface when we're looking at climate change. We look for other patterns or fingerprints of climate change, and for example, how the temperature has changed as we go higher up into the atmosphere, and the signal of that temperature change is consistent with human activity, but it's not consistent with any other cause. So these patterns are also important in establishing that it's human.
And as you say, the data from many different sources is very clear now that the Earth is warming. We see it in many different ways. How do you answer people? I mean, I myself had a little altercation with an Australian politician a while ago.
Did you get taken to hospital?
I decided that I would show them the data of the surface temperature anomaly. So it shows, as you referred actually to data from the 1940s and 50s and 60s. So these are data sets that were compiled a long time ago. And so there are people who will argue with the way that we process the data. So I wondered if you could just give a very quick overview of the challenges associated with processing
It is a
data.
large challenge. If we often see a temperature record going back to 1850, and over that more than 150-year period, the way we've measured temperature has changed. For example, sea surface temperature used to be measured by a poor sailor having to throw a bucket over the side of his ship and hauling it onto the deck and putting in a thermometer and measuring it, and even the type of bucket changed from wooden to canvas to insulated, and now temperature is often measured by the intake into the cooling water into the engines. And similarly on land, the way we've measured temperature has changed. And not only that, the distribution of temperature measurements has changed greatly. So again, if you go back 100 years, almost none in the Pacific Ocean. So we have to take those factors into account. And there's been a number of, there's 3 institutes, one in the UK, well, 2 in the UK, I should say, and 2 in the US who spend a lot of time developing these temperature records and adding in these corrections as they understood. And a few years ago, a rather skeptical group of scientists at the University of Berkeley didn't believe these temperature data sets and set about doing it themselves. And hey presto, they came out with the same answer that these other organizations had. And so we believe it's a very robust signal. And the IPCC, the Intergovernmental Panel on Climate Change, doesn't use the word equivocal very often or very likely. And the fact that climate has changed is unequivocal.
If you look at the data too, you find some, and compare one station with its neighbours, it's been found that some were using Fahrenheit instead of Celsius, and others, then you realise that this thermometer that used to be placed out in the country then is an urban site. And so that will change, and the corrections have to be made for those sorts of things.
I suppose it does say, it's worth emphasising, isn't it, that most of the science is in, we say correcting the data. So the idea that to scientists that you would plot uncorrected data on a graph is ridiculous. It's virtually meaningless, isn't it? That's where the skill and the knowledge lies. But it does sound, I think, in my experience anyway, it's somehow suspicious when you say we correct the data in this way.
But you have to homogenise the data sets. You have to make sure a measurement made in 1950 is equivalent to a measurement made in 1910, and it's a skill job, and these corrections aren't made lightly.
And also a really nice development recently is that some of these data sets are now coming out actually with error bars, accepting the fact that that you can't be absolutely sure what the global temperature was in any given year, but given what we know about our measurements and the errors in our measurements, and that seems to me, that's highly scientific, and I think really adds credibility to say, this is the range of what we can say.
And you can actually help put some more data into these models now with citizen science cyber projects. So there's a website which you should all go to because it's awesome, called Zooniverse. And they have this citizen science project called Old Weather. And they've digitized all the ship's records going back into the 18th century. And those exact same records, exact same records which you're talking about, they kind of had them written down on the ship's logs about the temperature. And you go in and pretend to be a ship's captain, and you can transcribe all the records. So people get very addicted to this. It's awesome. You should go and have a look.
Okay, well, let's move on to a very different question, actually, which I'll address to Kate first, which is from Colin, which is, what will the overall effect of climate change be on our wildlife?
Gosh, that is a really, really complex question. And it's a really active area of current research as well. So, I mean, firstly, the first thing to say is that you can already see the changes happening to wildlife populations around the world. And in the UK, we've been monitoring with citizen science projects a number of wildlife populations around the country, with hundreds of thousands of volunteers taking part in these citizen science projects. So there's quite a lot of evidence of northward shifts of the ranges of many species in the UK, stuff like Dartford warbler or the blue butterfly. But there's also natural colonizations from Europe as well, so like the southern emerald damselfly. And there's a mixture of evidence about the reactions of northern adapted species kind of retreating slightly at their kind of southern edges of their ranges. So there's kind of adaptations to the northern species too. So we see more pest and pathogen invasive species in this country. For example, I don't know whether you saw the stuff about ash dieback disease, but that was it's because of globalization. But once these pathogens get into the UK, they're much more adapted to any to spread because of the conditions being more favourable. There's also a report of giant Asian hornets, a first nest that's been found in this country, I think a couple of weeks ago. So the life cycle events are also changing. So flowers and leaves are coming out earlier, birds are laying eggs earlier, species are arriving from migrations earlier, the leaves are staying on the trees longer. You must have all seen that, so that's something that's impacting your lives now. So, but I guess the question is, well, what impact in the long term is this going to have? And that's a really interesting question, because you're basically asking whether species will decline to extinction, so populations will be so affected that there will a decrease in range size and then go extinct completely. And that's a very difficult question. And mostly it's because there's been a lot of studies, or a growing body of studies, about 100 studies that have looked at this individually, and only now we're kind of trying to pull this together in one analysis. So these data are now kind of looking at what's the total evidence. It's like in medicine when you ask about relationships between cancer and smoking, for example. That's the type of analysis that they're doing. So I don't want to alarm you or anything, but one of these studies that was published in Nature last year has a mean global extinction rate estimated of 1/6 of all species which would be impacted by climate change. And that means just their geographic ranges going below a threshold level. And the magnitude of these changes also is increasing with increasing temperature build-up. And some areas are more at risk than others, say New Zealand, Australia, and South America seem to be more impacted. But there are lots of uncertainties with this, and I think that's where the kind of work that we need to do is.
There's actually a related question from Anne, which is, I suppose, as species become extinct, new niches open up. And the question was, will new species evolve as a result of climate change? But then the comma, and will humans like us be around to see them, which is the more sinister.
So I guess if you're a species faced with a change in climate so that your habitat's not suitable anymore, you've kind of got three options, right? So you can either, move somewhere else, you can go extinct, or you can evolve. And I think the problem really is, the timescales involved here. So species have always adapted to their environments. They kind of run to keep up to adapt to environmental pressures. But can they do it fast enough or significantly enough to cope with climate change? And so, the evolution of crazy new things takes time. And so you need a number of generations and the variation to play on that, to evolve those things. But subtle adaptations to climate are happening all the time. So I don't know whether any of you have seen goldenrod, which is just a kind of daisy-like plant that most people have in their gardens. It's actually from North America. It was introduced here in the 18th century. And it's been naturalized across Europe, and the northern populations and the southern populations are now showing, so that's a few hundred years, are now showing significant adaptations to their local environments. And so if you translocate southern populations to the north populations where the north ones do fine, they do terribly. So you can see adaptations within that timescale, but really big changes take a while. And I fear that there are so many other pressures happening, so population increasing, probably not leveling out until 10 billion people on this planet, transforming all of the landscapes on this planet, all of the ecosystems. I fear that, invasive species and globalization, they kind of have this kind of heady cocktail of pressures, and climate change is adding into that.
But the end of the question, though, will humans be around to see this then? So actually, it's almost the opposite problem at the moment. There's a big lag, in other words, because you said the population's heading to 10 billion, which is going to increase the pressure on other species. But there's no suggestion in which we're going to vanish anytime soon. Is there a suggestion that the human population will be so challenged as climate change the effects increase that we will begin to see catastrophic reduction in the number of humans on the planet?
I think that's a very political question. I think there's been some work on...
It's Anne's fault, not mine.
There's been some work on kind of planetary boundaries and Earth systems, and I think it's been very popular in kind of policy circles to think about Earth systems as this kind of, we're trying to maintain this Earth system in some kind of steady state. So the steady state that's been around for 12,000 years or so in the Holocene, that's been kind of pretty stable in temperatures, can we keep everything into that steady state with these planetary boundaries? And then people have been trying to think about how you would monitor whether we've gone over those planetary boundaries. And I think that's very controversial, and I think Brian wouldn't...
Well, I was going to add on this really that climate change, as we see it, is going to add to all the other pressures in having 10 billion people on this planet. Is there going to be enough food in the right places, enough water in the right places? And what we've seen around historically and in the more recent period in the Middle East is that sometimes that climate that's making life difficult is just the last bit that makes conflict occur. Thousands of years ago, there would have been migration of humans, but we can't do that anymore. We have lines on maps. We have too many people, and that can't happen. But then the conflict is much more likely to occur. So it's adding to the other strains on this planet.
There's actually a related question to this from Stephen and by two Davids, apparently, on here, which is, have we gone past the tipping point, or a tipping point? Will it be possible for our climate to return? And the question says to its original state. So if you said we can define, we have to define when we'd like it to return to. But first of all, this idea of tipping point.
Okay, well, perhaps I'll take that then. We are not aware that the climate at this moment has passed something which is a tipping point in popular language, or maybe a bifurcation as a mathematician. But is there some irreversible change and we've gone to a new state, or something is going to happen that's essentially irreversible? Perhaps the one concern at the moment is some people think we might have gone beyond the irreversible melting of Greenland. It would take many thousands of years, but is that irreversible? But we aren't aware that we've gone beyond any of these. And I think we really are in the stage where if we can keep this change in temperature to less than 2 degrees as the Paris Agreement went, then we can hope that we can mostly cope with that. So it's really not, oh dear, we've gone beyond a tipping point, give up. It's actually, this is a call for action, because we may be able to get the climate to stay within bounds that we can handle. It's not going to return to some original state. I mean, the changes we've made will be there in the system for thousands of years. The ocean takes a long time for the bottom of the ocean to realize it's warmed up and communicate back. The carbon dioxide we put there will be in the atmosphere for thousands of years. So it's not going to just disappear suddenly, the impact we've had, but we hope we can keep it within a range of where the climate's been within the last 10,000 years, that humans and other species can mostly cope.
Yeah, I'd just like to emphasize this point about irreversibility. When you put CO2 into the atmosphere, it's got an incredibly long persistence, so a good fraction of it disappears within a few years, but then quite a substantial fraction stays there for thousands of years, and that's what makes this quite a difficult problem. If the CO2 we put into the atmosphere disappeared within a couple of weeks, which is the case for some of the things we put into the atmosphere, it would be a much simpler problem.
I just wanted to, just before I come to you, Oliver, just clarify. So this idea of a 2-degree rise. So could you just sort of define what that means? It's relative to what, and what is it? And also the question, where are we at the moment?
Either of you, I don't mind, I can take it.
Okay, I mentioned it, so so we're thinking about 2 degrees above pre-industrial, basically. So if you go back into the 18th century, perhaps, or 19th, even 19th. So we're sort of approaching, depending what happens this year, but generally we're approaching nearly 1 degree from that now. And the question is, are we going to add more than 1 degree to that? And the chances of crossing some threshold, the further we go, we can probably just cope if we keep it to this 2 degree, below 2 degrees, hopefully. But as soon as we start going 2 to 3 degrees, 3 to 4 degrees, there are many parts of the Earth's system which could actually say that's enough and we're changing to a new state. You know, you might get methane produced from the melting permafrost, or you might get a more local change where the storm track that used to hit Australia no longer does, so they don't get the winter rainfall, or the monsoon system in India. You know, so many billions of people depending on that. And the remarkable thing is how little it varies. But can we rely on that as we go through to these big changes? So we think we're probably able to cope just about, provided we stay within these bounds.
And we saw the carbon dioxide graph, about 400 parts per million or so now. So does that mean that if we stay there, then there's this inertia in the system and we just tail off and gently settle at 2 degrees? Or does it mean that we have to reduce that?
If we could hold it at 400, we'd probably be just about okay. But,
Yeah, we'd all be walking home.
and that's a challenge.
But it's within the environment of not just climate change is happening to this planet, there's a whole load of other things. So those planetary boundaries are kind of trying to address some of the other drivers, like the human population, food security, disease outbreaks, zoonotic disease outbreaks like Ebola, those kinds of things. There's a huge amount of uncertainty about where those boundaries are, and I think we're kind of playing a little bit with fire.
And just to be very clear, the 2 degrees, that's the surface temperature
Yes.
Yeah.
that we're talking about there.
That's right. That's the globally average surface temperature, which is not what anyone feels. In the northern polar regions, that might be as much as 10 degrees, particularly in the winter time. And it might be something. Most of the planet is ocean, and maybe that would be 2 degrees or even slightly below. But the actual rise in temperature is more in the tropical countries when you compare with the variability. So somewhere like Africa, a 2 or 3 degree change in Africa is huge compared with the variability that's been humans have experienced.
I just wanted to come back to, I think it was Anne's question, which led into Stephen's and the two Davids. But I do think there's a real risk of over-dramatizing and saying, will this drive humans extinct? Are we saving the planet? No, climate change is not going to drive humans extinct. If you want to really worry about human extinction, you should worry, and I don't think this could do it either, you should worry much more about the risk of nuclear war, which certainly could kill hundreds and possibly billions of people. Climate change is going to cause a great deal of harm to hundreds of millions of people. Maybe to billions of people. That's a terrible thing. It's not the same thing as extinction. It's not the same thing as I believe George Monbiot wrote in The Guardian the other day, sort of like endangering the whole planet. The planet is a pretty big, tough old thing, and will be going along, and we'll still have a lot of species on them, and it would be very sad, terrible if many of those species that we treasure were not among them. But those aren't the things at risk. The things that are really at risk are the natural world that we currently inhabit as it is, and our fellow humans. And it's really important to keep the focus on reducing the harm to people who exist today rather than this over-dramatized worry about the end of the world or the end of humanity, which is not, I think, what this debate should be about.
And there's a recent report from the Lancet on climate and people's health, and they said exactly that it's about how climate change is one of the biggest drivers of human health and well-being that's going to happen in the near future. And they're seriously concerned about all these papers are just Google them, they can read them for yourself.
There's again a follow-up question to this, which is what's the one change, if you could have one change, if indeed there is such a thing, that would have the single biggest impact to slow down or manage climate change, but let's say reach this 2 degree target, what would it be? And Helen asked that question.
Well, we have to target CO2 is the answer.
Yeah, reduce our CO2 emissions to zero as quickly as possible. The net CO2 emissions, and that's the answer globally. There's a more measured answer in terms of the UK, where the Climate Change Committee that I'm on has recommended to the UK government that we essentially decarbonise our electricity supply by 2030. So, reduce global carbon dioxide to zero, but we have a UK thing which we have a definite target to do. So the electricity you get from your plug should no longer come from a fossil fuel power station. So we've got to get to that situation.
But the problem with answering Helen's question in that way is that saying decarbonising the society, that's not one thing. The question was, is there one thing can be done? That is almost everything. That is changing almost every aspect of how modern life goes on, from how we build buildings.
I did only say electricity.
Well, even so. But that was also Helen's question was about what was the one thing we can do that will have most impact. And this is one of the really difficult things that Keith alluded to about climate change. It's not one thing. Ever since those steam trains started hurtling down the Great Western Railway, using fossil fuels is built into almost everything that people in developed countries do. Many people in less developed and least developed countries would like to be able to do some of those things too. Forget not that something like 1.3 or 1.4 billion people on the face of the planet have no access to electricity at all. It's not a question of just doing one simple thing. It's a question of changing an entire industrial ecosystem if you want to reduce carbon dioxide emissions. And I don't think that that's impossible, but I don't think it's a single thing, and I don't think it's easy.
This actually, unless anyone has anything else to add about reduced CO2, it does link into a question from Catherine, which is what are the panel's views on clean energy? So questions like nuclear versus wind or solar. Can we generate enough through, let's say, wind and solar? Do we need nuclear? These questions. So,
well, I must say, over the last 10 years, we have seen staggering progress made in terms of solar electricity. It's still, especially in a country which doesn't enjoy as much sunlight as Britain, it's still not as much as you would wish, but there has been staggering progress made. At the same time, the world is still running something like 78, 79% on fossil fuels. There is an inertia in these systems that is huge. And I think that the idea of decarbonising British electricity entirely by 2030, 2040 is ambitious, but just about plausible. The idea of doing it for the whole world is very, very strikingly different, even though, and there's no reason that the fact that it's difficult is no reason not to try. The question was also about nuclear. The problem with nuclear power, well, the problem with nuclear power, we could, and indeed some of us have written books. But the problem with nuclear power is really that at the moment it's expensive largely because you have to buy a huge amount of it to buy any of it at all. You can only buy nuclear power coming from very big nuclear power stations. That doesn't fit very well with the way that electricity grids and electricity consumption is developing. So there are places, and the other thing is that although I do believe that nuclear power can be run in a safe and reliable way, I also think it's very hard to do that unless you live in a democracy with a long history of questioning people and good independent oversight. So, I don't worry very much about nuclear power in Finland. I worry about it more in, say, China or various other developing countries where I don't think that the civil society to regulate nuclear power is really there. So the short answer is, yes, we have a number of clean power options, and we can push them into use faster and faster. We can also develop new storage techniques, and we can electrify some things that we don't at the moment use electricity for, like transport. At the same time, to do all that while emitting very little more carbon dioxide and thus giving ourselves a good chance of hitting the 2 degree or indeed the ambitious 1.5 degree target in Paris is more or less inconceivable.
So, Brian, you said you advised the government on this. So can you give us a brief flavour of the different policy options if we were going to decarbonise electricity by 2030, let's say? What were the options you gave to government?
Yeah, well, we have a high renewable scenario for 2030 where 65% of the energy would come from renewables. So that would be, the biggest player would be wind offshore, but there'd be solar and there'd be onshore wind, and maybe a bit of bio in there as well. So, and demand reduction is important, so that's always the number one, is actually being parsimonious with the energy we use. And storage is important, but we could get maybe up to 2/3 of our electricity, almost half our total energy from renewables by the middle of by 2030. But that would need then tipping the balance of actually valuing the carbon and making that very clear in the price of energy that people get.
And the rest would be nuclear, would it?
Well, there could be some nuclear, or there could be carbon capture sequestration. So that's taking fossil fuel power stations, which in the UK would be gas, hopefully, and it's stopping the CO2 escape, and then you take it out of the stack, and then you liquefy it and use it if you can, or else you store it underground. So it doesn't have to be nuclear. And there are some downsides of nuclear. Oliver's mentioned some. We're continuing to add to our radioactive pile of rubbish from the past as well. So, that's not necessarily, but we do need something as a base load, either nuclear or carbon capture sequestration.
It looks like we're going to get Hinkley Point now, doesn't it? Probably. And what's that? Was that about 6% of the?
Yeah, something of that order. Yeah.
So
yeah.
So, but that said, in the time that in 2030, I think quite a lot of the existing fleet of nuclear reactors will have closed down, or they'll have had to be extended considerably past their original design life. And it's not clear that we're going to get any more new nuclear reactors after Hinkley, though there are projects currently.
Certainly the only place
discussion.
they would be is where there are presently nuclear power stations, and maybe not all those.
Okay, so we move on to, I'll start with Keith on this question. It's how useful or important do you think climate model projections are for advising how to react to climate change? And that's by Annalise.
Yeah, well, they're absolutely crucial. I want to just be clear what a climate model is first. Climate models are computer models which encapsulate our understanding of the physics and increasingly the chemistry and the biology of the climate system. And their basis is in the well-known laws of physics, such as Newton's laws and the laws of thermodynamics we heard about at school. And our most complex climate models use some of the biggest computers on the planet. So what climate models are important for are telling us the things that we're certain about. And so one of those examples is the patterns of climate change the patterns of temperature change as we go into the future, and some of the things that we're more uncertain about. And that one example is the patterns of rainfall change as we go into the future. So they're important for distinguishing the certainties and the uncertainties. And these models, as well as including processes we understand very well, they also include processes which are harder to represent in these models. And one of those is cloud formation and dissipation. And clouds play a very important role in determining the temperature of the Earth. And there's some everyday examples. On a summer day, if it's cloudy, we know it's going to be cold because the clouds reflect sunlight, but on a winter's night, we know if it's cloudy, it's not going to be frosty because the cloud's trapping in infrared energy. And one of our biggest uncertainties in projecting climate change into the future is that different institutes develop different models with different representation of clouds, and they don't agree on how the clouds are going to change going on into the future. So it's important for policymakers to not only see what we're certain about, but also see that error bar of uncertainty.
Yeah, because I suppose one of the challenges a government has, I suppose what they're trying to ask you, maybe it's a question if they are trying, but they can say, how much is, I do this, it's going to cost, £20 billion or whatever it's going to cost, and the result is going to be this, okay? Is that right? And I suppose that's the challenge, isn't it? I suppose government wants to know how much is it going to cost to make this change, and what will that change mean?
That's right.
Are we anywhere near being able to answer those questions?
I think we can, but it's important that we put an error bar on our estimates to say, and Brian talked about the 2-degree limit before, and he actually put it in probabilistic terms. Because we don't know exactly how the climate will respond to CO2, we can't say for certain. We can say there's a 50% probability that this emissions scenario will keep us within 2 degrees, but if the climate turns out to be more sensitive than we think it is, because, for example, the way clouds change, then it could exceed it. So we always, and policymakers, they're often making decisions in the face of uncertainty. That's really what a politician's life is about, I think.
I think people do misunderstand quite how risky, how uncertain some of this is. I mean, the question of not knowing what the climate change that you get from a doubling of carbon dioxide is, and it's still a quite broad error bar. Would you say, 2 to 4.5, something like that? That's a big difference. As we were saying, 2 is something that with careful... 2 to 4.5 degrees of warming for a doubling of carbon dioxide. And, that's a big difference, because I was saying 2 degrees is the sort of thing that people think about being able to live with, and 4.5 degrees is really, really unpleasant for large parts of the world.
But politicians are used to making decisions in these manners when they are given a certain risk. I think maybe some of the difficulty with our economics modelling is they don't actually give the uncertainty. So we are being honest and saying, well, there's this uncertainty, and there's a certain risk of this and a certain risk of this outcome. Just to add to what Keith said, 2 of the models, they have been evaluated on past behaviour. They don't just run. They actually say, do they simulate what we've seen in detail, and in particular going back in time? And then the results from them aren't just taken as gospel, this is it. There's a range of behaviours, and people like me try and understand, now why is that model doing that, and can we have confidence in that? So we do have a range of things coming out of here, and what is being presented to the politicians is a risk with some idea of the confidence of what we're giving them.
Yeah, I think sorry.
I was just going to say that I think that these models, the climate change models, and that the way that you do them and set them up have influenced biological thinking as well, like in biodiversity science. So that we've been setting up and thinking about biodiversity changes on this global scale and including climate changes in these modelling approaches and getting more process-based, so putting actual responses to, individual responses to climate and land use change in these models. So I think that these models have actually helped us think about not just climate prediction, but thinking about what's going to happen for different species extinction. So I think that's also one of the kind of benefits of having this kind of approach and thinking about uncertainty in a more joined up way.
Okay, well, there's I suppose one of the questions, this is a question from Pam, sort of relates to this. So we're talking about 2-degree rise, 3-degree rise, and what we can do to adapt or to keep it there. One of the possibilities, of course, it sounds more science fiction, is geoengineering. And the question from Pam was, at the current rates of climate change, would geoengineering ever be able to counteract the human impact?
Well, yeah, thanks. I wrote a book about this one. I actually really did write a book about, and it's a really interesting question. So geoengineering just means a big technological change in the way the world works that's done for a specific reason, rather than sort of like as a byproduct of something else. And there are two types of geoengineering. There's actually big debates about what counts as geoengineering or what doesn't. But at the moment, it's widely seen that there are two types of geoengineering. One of them is sucking carbon dioxide out of the atmosphere. And one of them is stopping sunlight from getting into the atmosphere. Keith mentioned that there are particles in the stratosphere which reflect back sunlight. There are always some such particles. After a big volcanic eruption, there are more. Might it be possible to have a sort of like permanent layer of them and thus cool the planet slightly? That's the sunshine option. The other option is just to suck carbon dioxide out of the atmosphere and put it away somewhere. No one knows quite where, possibly under the carpet, possibly in disused gas fields, but somewhere nice and safe, trust us. And there are various problems with both of these things. But one of them is that although the technology is imaginable, no one knows the practical reality of doing it, and these things have side effects. And the question for me isn't so much, could you imagine a system that put little particles into the stratosphere and held the temperature at 2 degrees? Yes, you could. Would you be wise to use such a system if you didn't also do everything you possibly could to reduce carbon dioxide emissions at the same time? No, that would not be wise. The question isn't so much, can we make geoengineering technologies? Because I think that that's actually fairly easily answered that yes, we could. The question is, can we do that in a way that's safe and just and governable? So safe means not just can you do it in a way that you don't mess up other things. So for instance, if you put something up in the stratosphere, are you going to mess up the ozone layer? Or rather, should you not design what you put into the stratosphere so as not to mess up the ozone layer? If you change the Earth's temperature, you also have effects on its rainfall. The effects on rainfall caused by geoengineering are not exactly the reverse of the effects of rainfall caused by global warming. So you do not end up just going, it's not you go one step forward, one step back. You sort of like, it's more like a waltz. You go one step forward and then one step to the side, and then you sort of like, if you're like me, then just sort of like trip over, and it's all a bit ghastly. But it doesn't get you back to the same place. So the other aspect of safe is also, if you start doing this and other people object and those other people have armed forces which they are willing to commit to their objection, then you get into the sort of altercation that we very much wish to avoid. So the safety, it's a very open question whether you can do geoengineering safely. Other question is, can you do it justly? And by justly, I mean, are you going to take into account, in particular, risks that affect people who are not currently at the table? And that includes people in the least developed countries and people who aren't here yet due to not having been born. So there are issues of both international and intergenerational justice that need to be confronted when you start thinking about this sort of technology. That said, I don't think the fact that it's not obvious that you can do it in a safe or just way means that you should not think about how to do it. I think it was actually a very useful exercise to think about how you should do it, and I think there may be ways to do it that would genuinely be helpful, but they are not going to be helpful unless people have safety and justice just as high up in their minds as technology and capability.
It strikes me, I want to bring Keith in, but it strikes me that we're already doing it, though, aren't we? In the sense that we're filling the atmosphere with CO2.
I think
so. Some of those.
There's a guy who I respect very much who's done probably more work on geoengineering than anyone else in the world. A guy called David Keith, now at Harvard. And I think David came up very nicely with a response to that, which is, and we all know about the conflicts there can be between academic departments, but you're kind of insulting engineering if you equate making a mess with engineering. We are definitely making a mess of the atmosphere. Geoengineering is trying to do something rather more targeted with a deliberate effect. And I think there is a case that you could say that there's been other geoengineering, but it's not in the climate. I'd say that the way that we've changed the nitrogen cycle on the planet might be argued to be geoengineering. But there is, I think you do have to make a distinction between stuff that you've thought through and deliberately trying and might fail to do, and stuff that you just fell into doing because you had no idea that steam engines did that.
Mm-hmm. Yeah, I think the point you made about the geoengineering calculations so far that have gone on within our climate models we talked about before, and actually we've learned quite a lot about the climate system from those experiments. But I want to address another issue about this putting tiny particles in the stratosphere. And we know from our understanding of past volcanic eruptions, like the Mount Pinatubo eruption in the Philippines in the early 1990s, that these particles only remain in the atmosphere for about a year. And we talked before about a significant fraction of the CO2 we put into the atmosphere persisting for centuries. And so if we went down the geoengineering route, we would be committed to replenishing those stratospheric particles continuously. So it wouldn't just be a one-off, it would be a continuous process, and this would be an intergenerational thing. We would be committing future generations to continue to do that.
And that's somewhere where the two different types of geoengineering seem to sort of like have a certain synergy, because one thing you could say is that gives you time to use your giant sucking machines, specifics not known, to get rid of the carbon dioxide. And one thing I should point out is that the giant sucking machines that I'm slightly making fun of are in fact already embedded in policy. Most of the scenarios that deliver all the scenarios that deliver 1.5 degree likelihood from where we are now, and an awful lot of the 2 degree scenarios, involve in the second part of this century some sort of process for actively removing carbon dioxide from the atmosphere, what's sometimes called negative emissions technology. And I worry about this because now people think that technology will exist. They also think, well, maybe we can make that technology do a bit more. And one of the problems with various ways of doing this technology, the one that's most talked about is to use bioenergy and then use the carbon sequestration and storage that Brian was talking about. One of the problems with this, with like burning biofuels and putting the carbon dioxide under the ground so that you're net taking carbon dioxide out of the atmosphere into the plants to power stations to reservoirs under the ground. One of the problems with this is it takes up huge amounts of land to take out carbon dioxide from the atmosphere that way. And huge amounts of land are kind of what biodiversity is about. If you take away huge amounts of land, what are you going to do with the things currently using that land? And I think that sort of carbon dioxide reduction could have really terrible impacts on biodiversity. Arguably could have worse impacts on biodiversity than an extra 0.5 degrees of warming.
When you think about these geoengineering things, I think it makes stopping the CO2 getting in the atmosphere in the first place seem like a pretty good solution.
Absolutely, it does. But without wanting to reflect, how's that working for you at the moment?
Doing okay.
No, we're not. Actually, Brian,
in the UK, we're doing all right.
Yes, but the UK is a rich, developed nation which can afford to do all right. I don't think we as a planet, if you argue that we as a planet are doing okay, I think that's not quite fair.
We're developing the technologies that must actually be transferred around the world, and that's the crucial step with the funding and the technology transfer.
Absolutely, but you don't think that's happening fast enough to avoid 2 degrees, do you?
I think we're really pushed on that. I think the Paris Agreement made me hope that there really is an international will to make that 2 degrees a limit. At the moment, that what they've agreed on is more like 3. But given the necessity for this, the pressures for development, which is quite right, how is somewhere like India going to get electricity to its villages? It's obvious how it should do it, by having solar there, and we should help them do it.
Absolutely.
There's actually a related question from Maggie, which is, we're talking about, I suppose you're referring to the difficulty of getting global agreements on what's clearly a global problem. And the question is there anything that could real people do something? Do you see that behavioural change of individuals working together rather than governments could make an impact? Or does it really have to be absolutely an intergovernmental level that we're going to solve this problem? Or both, in fact?
I'll have a start. I think it has to be all levels. There's certainly no way we should step back and say, all right, okay, the governments of the world are saying they're doing it now, that's it, we can get on with whatever we want to do, because it won't happen unless ordinary individuals everywhere around the world say we want this to happen. So I think at every level, the individuals have to say that. We elect politicians, maybe that's one of them, we elect politicians and we can put pressure on them. We have various levels of government. In the UK, the devolved administrations, for instance, Scotland's doing all sorts of interesting things in terms of trying to do low carbon.
This might be your mic.
It's my mic. Okay, right. Let's see if I can get away from the crashes now. Where do I start? Anyway, all levels are required to do something. Individuals were incredibly important here. I've often had the argument when I've given talk, well, the UK is only 1 or 2% of UK emissions, so why should we bother? The Chinese are producing all their emissions. Absolute rubbish. Well, you go to China and say, well, we've got this Climate Change Act, and we're really working on this. They're really impressed. That's been very influential on them in their decisions, and they've come to the table now. China is really a major part of the solution, whereas it was looked on as a major part of the problem. But we have a lot of influence from what we do here, and the technologies we developed, as we said before, in doing that, are incredibly important to send around the world.
Actually, I should say that question was asked by Maggie, but there are 2 questions here which are related, I think, to people taking responsibility themselves and putting pressure on their governments. One of them, which I asked Kate, which is from Magdalena, is can we discern climate change now in our everyday lives when we look out of the window or go for a walk? Can we see those effects? Are they becoming obvious?
Yeah, I think so, and I did say this before in one of the other questions. You can see plants responding, the natural world responding to changes, and you just need to look outside your window to see this. And the health problems of climate change are also becoming more pressing as well. So I think that this isn't just some abstract thing. This is happening to us now, and we need to take this and take it to our politicians to get them to start doing more to stop the emissions happening. I think it's really critical.
And there's the very obvious news story this week, the hurricane that's gone through tragic events in Haiti and then on into North America. So I know there's often been a lot of debate about whether you can point to these extreme weather events or the frequency of them and say that is a signal of climate change. So Keith, what can we read into these events like the one we're seeing playing out now in America?
Well, yeah, I mean, taking an individual event and attributing it to climate change is always difficult. So and it's a challenge that the climate science community is taking up. But I mean, there's just one example in the UK over recent years. There's a long-term data set called England and Wales precipitation data set. And colleagues of mine at Reading have analysed that. And if you look at the really intense rainfall events lasting for several days, then over the past 15 years, we've had events in the year 2000, the year 2007, 2008, 2012, 2014 and 2015, which were almost unprecedented in the record going back 17 years. So these are kind of strong rainfall events lasting several days. And so there's been you know, we can't absolutely say that's climate change, but you wouldn't bet against it. And I think Brian's probably better placed to talk about the hurricane.
Oh, yeah.
I think we have a picture of,
There it is.
this is Hurricane Matthew as it was just about to hit Haiti a couple of days ago. And again, the amazing power of these storms dwarfing any power of anything we do. Now, those storms are damaging with the winds, but they're also more damaging usually with the surge of the ocean that goes with them. Those winds drive the ocean. The very low pressure helps the sea rise as well. And those surges, Katrina in the States was a 6-meter surge. 6 meters, you imagine that. And I think Sandy was 3 meters. So that those, and there's a record which is way bigger than those as well. But, and then the heavy rainfall, over a meter is not an uncommon thing with one of these tropical cyclones. I think the record is 6 meters of rainfall with a tropical cyclone. So you're being battered by the wind, you've got this surge of the ocean, and you've got all this rain coming down. These are just huge events. Now what they feed off is the warmth of the ocean. They only form over warm tropical waters. And in fact, the waters that this have passed over are 1 or 2 degrees warmer than normal. And that's the previous normal for the previous 30 years. So around 30 degrees, those waters. And that makes the energy much more available, because the energy for the storm comes from the warm ocean. And that then leads to, is this going to change, or are they changing? And it's very difficult, because they come in these sort of very extreme numbers just now and then. But the evidence is that for the extreme tropical cyclones that they are increasing. Someone's put the number of 40% over 50 years. So the extreme ones seem to be increasing. Now, with climate change, there's been a lot of discussion about this, but the order 1 hypothesis is if the system warms, the ocean warms, there is more energy available for the extreme tropical cyclone. Now, they depend on other things, but that's the evidence we have at the moment, and there's nothing in the models to contradict this, I think, in the latest ones, that the extreme tropical cyclones are liable to increase.
And also, indirect effects too. So if you put more particulates in the atmosphere, you're breathing terrible air, so that the impacts of having particulate matter in our cities, for example, are breaking most of the European laws on air quality. So these are also having an effect on us right now. You know.
This is from vehicle emissions.
Yeah.
So just going back to Matthew, though, there's another point which Keith was talking about with me before we came on stage, which is the thing that Matthew also shows you is how much adaptation and resilience comes with being in a more stable, richer country. Look what Matthew has done to the poor people of Haiti compared to what it is doing to the people of Florida. And I was recently in Florida, and it's no picnic, I'm sure. But at the same time, the devastation that happens when something like this happens in a less developed nation is incomparably worse. And that's something that our whole conversation about climate hasn't really mentioned much at the moment, which is when we talk about climate change, there are a number of responses. There's mitigation, which is reducing emissions rates. There could possibly someday be geoengineering. There's also adaptation, and adaptation is a very important part of climate response to in all the world, but particularly in developing countries. And it's worth bearing in mind that people aren't particularly well adapted in all parts of the world to their current climate, let alone to any changes in the climate. And there is a fourth thing, which is suffering, that these things do bring about terrible human suffering.
I think actually I totally agree with that, but sometimes the richer countries think they're immune. And I used to give talks and say, what would it take to take the US to be serious on climate change, and perhaps a tropical cyclone over Florida or New York or something? Well, look what happened to New Orleans, wiped off the map just about, even in a rich country. So we're all of us vulnerable, but the vulnerability is much higher in the developing world.
That's true, and it would be hard to draw a line between... No, that's absolutely true. I was just going to say, rather sadly, it would be hard to draw a line between Katrina and any change in American climate policy.
So this might bring us, actually, we're running out of time now, but to I think what's going to be the last question, which is from Sylvia, which is, related, I suppose. How do we better bridge the gap between the scientific research on climate and government action on climate change?
Well,
That's a really hard question.
In a minute.
yeah, in a minute. I mean, I've tried to do this influence at some times, and I mean, it might help if our whole society in the UK had a better image of science and a better education in science, because I think at all levels there is not enough scientific background to really get this this agreement one's got to get through society of what's going to go happen. I mean, I think the present Parliament has 27 MPs with science and technology degree, and none at the PhD level. There was one PhD, but he lost his seat in the last election. So there isn't a great knowledge, and I think if you go to the cabinet, you'll find it's probably zero. I'm going to be checked on that, I'm sure. So we are dealing with a problem there in terms of actually just what can you use as a sort of background information to make this, get the information through. But we do have in the UK the Climate Change Act, and I'm on the Climate Change Committee, and we are recommending that I have a proper microphone.
That was, I was going to say that was Donald Trump's excuse in the last debate, wasn't it?
Don't say anything about women.
I'm not going to say anything like Donald Trump. Yeah, okay, I'll keep off the politics. Yeah, so we do have the Climate Change Act. The Climate Change Committee makes its recommendations. It's 5 out of the 8 members of the Climate Change Committee are PhD level in science and technology, and the information we give is based on a high level of input in this area, and we do find that we can actually communicate that through. So I think having the right structures where the information can get across enables that information to get there, but it will certainly be much easier if the level of scientific awareness was higher in all levels of community.
Okay, so yeah, it might be good if we go along the panel actually with the last question.
I think it's up to the scientists to be a bit more engaging as well. So it's not just people, not engaging with science, but science engaging with people and understanding that we're fairly normal people, and that that we want diversity in our kind of scientific community. We want equal numbers of unrepresented groups, like women and other unrepresented groups on these panels. I think it's kind of up to us, really, like having meetings like this where loads of people come and you can kind of engage with us. I think that those are the things that we need to be doing more of. So it's up to us as well, not just educating people to be interested in science.
Yeah, I'm not sure I see this as as a core problem, because I think I'm not entirely happy with the idea that everything's better if the scientists can push a policy that they like. I think that understanding the science is crucial, but I also think that there's a reason why politicians are called politicians, is they do politics and they do trade-offs with other things. And the way to get politicians to act more in the way that you want is not necessarily to increase their scientific awareness. I don't think that there's a clear, not least because the scientific awareness really has to be in the sort of policy advisors' place. The politicians make choices and make trade-offs. And if you want them to act differently, you need to let them know that they will want for your support if they make certain sorts of decisions. I think that the politics really has to be tracked mainly politically.
Yeah, I want to talk about some just messages of hope from other environmental problems we've had, and I want to focus on the ozone depletion problem, the stratospheric ozone depletion, which was a very big issue in the 1980s and 1990s. And solving that problem was a very good example of the healthy interplay between scientists, government, and industry, which led to the United Nations Montreal Protocol. And this led to a very rapid phase-out of emissions of the CFC, or chlorofluorocarbon gases, that we were using in our fridges and air conditioning. And these were the gases that were destroying the ozone layer. And although we've now almost completely banned emissions of these gases, and although it will take 30 or 40 years or maybe a bit longer before the stratospheric ozone layer completely recovers, we're beginning to see that recovery now. So there's no doubt that solving the stratospheric ozone problem was a much easier problem than solving the climate change problem, but it does show how scientists, government and industry can work together towards a common goal.
Yeah, I wonder whether anyone wanted to pick up on what Oliver said just at the end briefly, because this is one of the central challenges, the centre of the question actually. It's almost like if only the politicians in society would do what we tell them, everything would be fine. There's a sense of that. Oliver makes a good point. So I was going to say that's not necessarily true. I might actually believe it is, but I'm not trying to. What's the?
Yeah,
it's a delicate problem, isn't it?
What we've got to do is make sure that we get a scientifically based view in there, but the decision is a political one. On the Climate Change Committee, we've got to take on board issues of poverty, the availability of electricity, water-to-all, the UK economy, all these sort of things come into play, and the scientific input and technological input is just part of the scene there. But it's interesting that actually the UK was leading on this issue from the time Margaret Thatcher, with a science degree, actually took it up before anyone else in the world. I didn't like everything she did, but she was amazing in this one. She took it up and led that one back in 1988 in a speech at the Royal Society. And there was the scientist who felt able to take that issue on board.
Anyone else? There's the last follow-up question. We've got about 2 minutes left. Brian, because you said you wanted to avoid politics, I'll start with you on the last question, which is from Gay. It says, does Brexit have the potential to undermine international collaboration regarding climate change?
That was a mean question.
The answer to that, the international collaboration will occur. What it's done, I think, is made the UK contribution to that much more questionable.
Well, I would...
Kate.
Sorry. I think there's been some talk in the kind of biodiversity conservation community that although we don't, a lot of people don't like the fact that we're Brexiting, maybe that it's an opportunity as well to understand our relationship with the environment a bit better, so that we can put more protection in for the environment and understand emissions rather than less. So maybe it's an opportunity. I don't want to be too optimistic, but maybe it's an opportunity rather than a terrible disaster.
In the sense of what? Agricultural practices?
Yeah, because one of the drivers at the State of Nature report a couple of months ago came out with that intensification of agriculture has been one of the main drivers of biodiversity declines in the UK. And perhaps if we could have a more joined up policy with farmers and talking in collaboration with them, and how we manage, multiple problems like food security, but also managing our wildlife populations, it might actually be better.
Okay.
Well, we've talked a lot about uncertainty in climate change here, and perhaps the one word I would say that's the biggest problem with Brexit at the moment. It's not whether Brexit is a good or a bad thing, but the uncertainty. It's uncertain whether we'll have access to European funding for our research. It's uncertain about how we will collaborate with partners in Europe now. We have a very strong and healthy exchange of scientists between the UK and other countries, and it's uncertain how that will be at the moment. So it's really the problem I see at the moment is the uncertainty.
Oliver.
I think there's a sort of like policy answer and a political answer. Policy answer, I think, is that if you're going to a much more heavily renewable electricity system, which we have to, it does really help to be part of a big system, because If the sun's not shining here, it's probably not shining in Slough, but it may well be shining in Stuttgart. And so if you can move electricity around more easily, then you can go renewable more easily. And I think there are various European projects for increasing energy infrastructure, and I think we can be fairly sure that at the margins we're going to be less involved with those than we were before. And this also actually goes to the question of possibly doing carbon capture and storage. There's a lot of talk about using the North Sea as a resource there, and again, that would be made more difficult. I think more worrying for me on a British point of view is that the political agenda of the people who were keenest on Brexit tends to be very similar to the political agenda of the people who are least keen on action on climate change, people like Owen Paterson or Peter Lilly, who are rather dubious about the benefits of acting against climate change and also dubious about the benefits of being part of the European Union. And I think the evidence of the Tory party conference is that that side of the Tory party is doing pretty well at the moment. And so I think in terms of domestic climate policy, the ascendancy of that particular view is likely to be quite damaging.
I just wanted to add one thing about something we should have been very proud of, that the UK actually led for the EU in the Paris negotiations. Now, you probably weren't aware of that, but there was the UK leading for this huge block of nations on this important issue, and the influence that provided for us was huge. And of course, that won't be available to us in the future.
Okay, well, I'm just going to say that I'm glad if this was a BBC programme, I'd have to try and provide some balance to that, but this is the Royal Society, so I don't. It's very good. Thank you. I'd just like to, unfortunately, we've run out of time, so I'd like to mention that we didn't have time to answer all the questions, but some of the other questions that we didn't have time to answer will be filmed, and we're going to put the video answers available online at the Royal Society soon. So if your question wasn't asked, then you'll be able to see the answers there. I'd like to thank again Sir Brian Hoskins, Professor Kate Jones, Oliver Mawson, and Professor Keith Shine. And so actually, we'll thank the panel, please. Thank you. Thank you again. And just one last thing, I should mention that there's a superb document, I think, which is available on the Royal Society's website, which is a Q&A on climate change. And I think that was done with the National Academy of Sciences in the United States. And that is at royalsociety.org/climate change. But thank you for listening.